Hi everyone, I'm Ren from Huawei and OpenEuler community. I'm so glad to attend the second Zephyr Developer Summit and share my presentation today, the meetup between OpenEuler and Zephyr. Okay, at the beginning, I want to make a brief self-introduction first. I have been in Zephyr community for almost 7 years since it started in 2016. Now I'm working in Huawei as an embedded OS technical expert, which is my job title. My main work now is around OpenEuler. I'm the member of OpenEuler technical committee responsible for the embedded scenario and the maintainer of SIG-Zephyr and SIG-Zephyr. Here, SIG means Special Interest Group, just like the work group in Zephyr. I'm also the architect of OpenEuler Embedded, which is an embedded Linux distribution based on the OpenEuler. I will share more details about OpenEuler and OpenEuler Embedded later. In my spare time as Zephyr project ambassador, I'm still devoted to the introduction and promotion of Zephyr in China. Before I joined Huawei, I was in Synopsys Wuhan R&D Center, worked on the embedded system software for Synopsys DesignWell ARC processor. I got connected to Zephyr since 2016. First time worked on the ARC processor support in Zephyr. I saw the fast growing of Zephyr project in the past 7 years from a startup project to a top IoT OS platform. Before Zephyr, I also tried to set up an IoT platform named Mbug OSP, which is a little similar to the ARM Embed platform. However, compared with Zephyr, Mbug SP, that obviously doesn't make any sense more. So later, I fully jumped to Zephyr. In university, I started my career in embedded system and got a PhD degree, and took my open source journey in Japan. From 2011 to 2016, I was the special member of Topos project, which is an open source real-time operating system platform, very famous and popular in Japan. It is the successor of the well-known iTron project. Okay, here is the agenda of my talk today. First, the origination of OpenEuler, then the extension of OpenEuler on embedded scenario, OpenEuler embedded. And having OpenEuler embedded, then we have the chance to set up SIG-Zephyr. I will introduce why we set it up. Finally, the specific cooperation field of OpenEuler embedded and SIG-Zephyr, the OS mixed criticality deployment. What is OpenEuler? OpenEuler is a mainly Linux kernel-based unified OS distribution platform. It is initially founded by Huawei in 2019 and later donated to the OpenAtom Foundation last September. So it has a little similar. So it has similar openings like Zephyr project, founded by companies like Intel, NXP, Synopsys, etc., and now under the flag of Linux Foundation. OpenEuler, also similar to communities like Debian, aims to be a top upstream platform. As we know, a lot of sub-platforms and distributions derive from Debian, for example, Ubuntu. Debian and the Debian variants are widely used in areas like desktop, embedded server, edge, and other scenarios. Until now, OpenEuler covers 4 main scenarios: server, cloud, edge, and embedded, where server and cloud are supported at the beginning. Edge and embedded scenarios are added in last September. In OpenEuler, all 4 scenarios share the same package repo, for example, the same kernel and other software components like glibc, Linux utilities, OpenSSL, and even CVEs. All package repos are maintained in Gitee, a platform like GitHub, and also have mirrors in GitHub. Different scenario OS are created and released through composed systems like OBS, Yocto, and other tools. So OpenEuler is an OS platform supports multiple architectures. You can find diverse computing architectures here: ARM, x86, RISC-V, Power, Long Arc, which is a Chinese architecture, has some relations to the MIPS at its early stage, and SW64, which is also a Chinese architecture, has some relations to the DEC Alpha architecture. Around the supported architectures, you can find a lot of chip vendors. Some are international companies like Intel, AMD, and recently Marvell. More are Chinese vendors. In all supported architectures, ARM64 and x86-64 are in Tier 1. You know, OpenEuler starts from server and cloud area. These two architectures are widely used in server and cloud area, but don't worry, the quality of the support of other architectures is being greatly improved as more and more force join in, especially for RISC-V. As I said before, in OpenEuler, all the four scenarios share everything that can be shared: kernel, software package, and the infrastructure. We do collaborative development of one set of code and the release of 4 images for all scenarios. Besides original codes from upstream, OpenEuler also does a lot of innovations. In kernel, currently OpenEuler has a 5.10 kernel as a baseline, and does a lot of characteristic work in file systems, scheduling, memory, and reliability. And considering the different requirements of different scenarios, different features are also developed. For example, Isulat, a lightweight container engine; StratoWord 2.0, a lightweight virtualization. Especially in embedded scenario, we have mixed criticality with Zephyr as partner, real-time enhancement, soft bus, and these features I will make a further introduction later. After 3 years, OpenEuler grows to be a vibrant community as Zephyr did in the past 7 years. In China, OpenEuler is the #1 OpenOS community. Here are some statistics about OpenEuler until this May. We can see users 500,000, contributors 8,000 plus, organization members 330 plus, SIG 97, and SIG-Zephyr is one of them. Repos nearly 9,000, means at least more than 8,000 software packages are supported and maintained in OpenEuler, and lots of pull requests, issues, comments. These numbers are updated every day. However, compared to the mature communities like Debian, Red Hat, OpenEuler still has a lot of work to do. And for more information, you can scan the QR code at the right corner. In OpenEuler, there are 2 official releases per year, one in the end of March called 03, one in the end of September called 09. There are 2 types of release versions: innovative versions and LTS version. As the name shows, innovative versions quickly integrate the latest technical achievements of Euler and other communities. LTS versions put more focus on stability and quality. Each 2 years there will be a LTS version, just like Zephyr does. At the beginning, OpenEuler used 4.19 kernel as a baseline, and now switched to 5.10 kernel. The just released OpenEuler 22.03 is a milestone, as it is the first all-scenario LTS version. For release and image info, please scan the QR code. Totally, OpenEuler welcomes more groundbreaking innovations. OpenEuler is an open platform and a community. After it's donated to OpenAtom Foundation is also vendor neutral, as Zephyr is. OpenEuler welcomes all kinds of contributions. As I introduced just before, there are already different forces working together in OpenEuler. Companies, universities, personal developers, for example. For hardware companies, they can provide hardware optimizations, compatibility certification, new feature enablements. For OS vendors, they can do their own release commercial distributions, build up business model, and contribute pull request. For independent software vendors, they can do applications certification, full stack solution, and queuing. For normal users, they can build characteristic distribution according to their own needs and raise requirements and issues, contribute codes. So welcome to join the OpenEuler community to start your innovation journey. Okay, let's make a brief introduction of OpenEuler. In last September, OpenEuler was upgraded to a ubiquitous OS platform for the digital infrastructure. Two new scenarios are covered, edge and embedded. Although OpenEuler embedded is young, but it has a strong background. Some part comes from the solid base of OpenEuler. Some part comes from the leading force of OpenEuler embedded, Huawei. Huawei is a leading technology driving company in ICT field. Here, ICT means IT, information technology, and CT, communication technology. As we know, CT is a typical and important application field of embedded systems. Huawei already has a very strong accumulation in embedded system, which powerfully supports millions of products like 5G base stations, routers, switch, and storage devices. As we know, one hand, Linux is more and more popular in embedded systems, especially when embedded systems becomes more complex, more connected, and smarter. On the other hand, Linux is not the one in embedded system. It can't meet all requirements like real-time, safety, low power, which is the field of RTOS, even bare metal. Therefore, we define OpenEuler Embedded is a Linux-centric, comprehensive embedded software platform. Linux is important and necessary, but not everything. In our view, OpenEuler Embedded is just like a solar system. The embedded Linux is the sun. Planets are RTOS, key embedded hypervisor, even bare metal. As the sun of the solar system, OpenEuler Embedded provides unified build, rich features, ecosystem, interface, etc. to attract other planets. Different planets provide their own characteristic features and ecosystem. For example, for hard real-time, you can choose Zephyr. Security, you can choose TFM. Low power, embedded virtualization, and other components. Let's go further to see the architecture of OpenEuler Embedded. The blue part is the scope of OpenEuler Embedded. In runtime, above the hardware is a component called Embedded Flexible Foundation, which could be based on the technology of virtualization or TEE or others. Its main work is to provide strong quality of above OS or runtime and the low-level management of physical resources. Above the embedded flexible foundation is Linux kernel and RTOS. Although OpenEuler Embedded shares common Linux kernel with other scenarios in OpenEuler, it will do specific configurations, patches, and optimizations according to the requirements of embedded systems. For example, the RT-openAMP patch, fine-grained configuration, the memory footprint optimization. For RTOS, there is no standard option, but here we chose Zephyr as OpenEuler's or as OpenEuler embedded's good partner. We will develop technology named Mixed Deployment Framework to integrate OpenEuler embedded and RTOS. And SoftBus is a network technology collection to connect different devices in local network. It comes from OpenHarmony community, a brother community of OpenEuler. We port it to OpenEuler and to connect OpenEuler and OpenHarmony ecosystems. The typical application fields of OpenEuler embedded is industrial IoT. For example, PLC, robots, energy, where a general OS like Linux is required. And we want to build a solid common base to attract users, vendors to construct their application on OpenEuler embedded with application-specific know-how. And because of the limited resources, it's not easy to do work like debug, trace, and performance queuing in embedded systems as similar work in PC server. Therefore, the DFX, which means design for X can be debug, performance, or trace, is a very important focus of OpenEuler embedded. We want to improve the development experience of embedded Linux through a good DFX framework. Besides runtime, the infrastructure, including tools, build system, CI/CD, is also very significant part of OpenEuler embedded. The infrastructure is not shiny as runtime features, but is the backbone of a good platform. It supports daily work. Later, I will make a further introduction to the build system. Okay, SoftBus. There is no doubt that connection is top one word in embedded systems facing the trend of IoT. In fact, SoftBus here is a collection of networking technology coming out of our brother community, OpenHarmony. It is designed to simplify the connection and the management of node devices, and is already widely used in consumer electronics, a little like the recent very popular MAT protocol. Here, we work with OpenHarmony community to port SoftBus technology to OpenEuler to interconnect OpenEuler ecosystem and OpenHarmony ecosystem. The main job of SoftBus is first the auto detect and connection of devices, then the interoperation of devices, and further the resource sharing like computing, storage, human-machine interface. Through SoftBus, we can easily connect OpenEuler and OpenEuler device, OpenEuler and OpenHarmony device in a unified and scalable way. Next, unified build. What's the difference of Linux-based system among different scenarios? From a high-level abstract viewpoint, a Linux system can be a Linux kernel plus rootfs, which is a combination of lots of software package plus scenario-specific configuration. So we have a unified infrastructure to construct Linux system for different scenarios? For all I know, currently there is no such a system or tool can do that. In server or desktop area, tools like OBS or Koji are used to build a big OS with thousands of software packages. They do a good job in large-scale distributed build, but not suitable for jobs like cross-compile and fine-grained configuration, which are required in embedded and edge scenarios. Also, not suitable for personal developers because of the complexity of deployment of these tools. In embedded scenarios, tools like Yocto or BuildRoot are used to create fully customized embedded Linux through cross-compile, but their focus is on local building and has poor support for large-scale distributed build to build thousands of packages quickly. Server and Server and cloud are the first two scenarios supported in OpenEuler. OBS and RPM build are the core of build system. So the build of more than 8,000 password package in OpenEuler are described in RPM spec format. So now edge and embedded scenarios come in. We have to use Yocto because of the requirement of cross-compile. So if OpenEuler embedded wants to share everything with other scenarios, there will be a big challenge. Should we write BB files for more than 8,000 packages and maintain the BB files and the spec file at the same time? I mean, it won't be welcomed by the community as the BB file and the specs file are so different. So that's why we hope to have a unified infrastructure to cover all scenarios. It's very challenging and difficult to reach the goal in one shot. However, we want to take out the first step. So in front end, we want to get a unification in the build metadata like repo name, version, summary, dependency, etc. and describe this information in an easy to maintain format like YAML. Then we use a user interface tool to do metadata convert for different backend. For embedded and edge, we convert to Yocto systems. For server and the cloud, we convert to OBS systems. When we get enough experience and preparations, then we can have a new scalable backend to replace Yocto and OBS. And it will be very challenging, but also very meaningful. In this March, OpenEuler embedded set sail and has its first official release. Here are the abstract of this release: 5.10 kernel, premium RT patch, QEMU and Raspberry 4 support, soft bus, security enhancement, basic infrastructure. And we can see that the mixed deployment of OpenEuler plus Zephyr is a highlight feature, which I will show later. Although OpenEuler is still very limited, few DSPs, few software packages, I'm confident that OpenEuler can grow to be a good and open software platform, just like Zephyr started 7 years ago. Okay, that's for OpenEuler embedded. So with the coming of OpenEuler embedded, now we have a chance to bring Zephyr in. The bridge is SIG-Zephyr. So why do we set up the SIG-Zephyr? Generally speaking, setting up SIG-Zephyr is a win-win approach for both Zephyr and OpenEuler. Let me explain that. After 7 years evolution, Zephyr project has grown to be a top IoT OS platform worldwide. Platinum members like Intel, Google, NXP, and other companies. 10,000 plus pull requests per year. 1,000 plus contributors. Website, mail list, Discord, social media, YouTube. So good, so hot. But the ecosystem and the popularity of Zephyr in China is huge different. There are still no Chinese companies in the member list. There are only WeChat and QQ group to discuss Zephyr. For such a situation, there are a lot of causes. Because, for example, language, time zone, network access, competition from local IoT platforms, relative sharp learning curve. So it's a good opportunity for Zephyr to cooperate with OpenEuler, the top OS community in China, to set up Zephyr China ecosystem and accelerate the promotion and the usage of Zephyr. For OpenEuler, in last September, OpenEuler upgrades to OpenOS for digital infrastructure and the current embedded scenario. That's why we have OpenEuler embedded. So OpenEuler community also upgrade to the ubiquitous OS community. It welcomes all kinds of innovation and cooperation. So SIG-Zephyr will bring in a high quality of little OS for OpenEuler Linux in embedded scenario, but not limited. And Zephyr has similar develop way, flow, coding style, and like Linux. Most important, vendor nature. Also, the position of Zephyr is fits where Linux is too big. Internationalization is a very important goal of OpenEuler in the future. Cooperating with Zephyr, a worldwide top IoT OS platform, clearly will benefit its goal. For example, talk OpenEuler story in Zephyr project's channel. So my talk today in Zephyr Developer Summit is a good start. Based on these reasons and the support from OpenEuler and the Zephyr project, we successfully set up SIG-Zephyr last September. Here are the vision and the work scope of SIG-Zephyr. Vision. Number one, introduction and promotion of Zephyr in China. Attract more users and developers. Number two, a bridge to connect OpenEuler community and the Zephyr community, devoted to the localization of Zephyr in China and the internationalization of OpenEuler in worldwide. Specifically, SIG-Zephyr will do the following work and already has some initial achievements. Maintain millions of Zephyr released and keep sync with upstream. Provide a local way to share and discuss Zephyr experience. Contribute Zephyr-related Chinese documentations, for example, blogs, wikis. Hold periodical online meetings. Now we have a SIG-Zephyr meeting per month. Attend events held by OpenEuler and Zephyr, for example, OpenEuler Developer Day, Zephyr Developer Summit. And create demos of OpenEuler embedded plus Zephyr. And do interaction of other SIGs, e.g., for example, SIG Yocto, SIG Industry, and SIG Embedded. Next, let me share the possible scenarios of OpenEuler plus Zephyr in technology. Number one, AMP model, where Linux runs on some cores, Zephyr runs other cores, which can be heterogeneous. The physical resources are statically allocated between Linux and Zephyr, and they communicate with each other through shared memory and inter-processor interrupt. AMP mod is also the first cooperation scenario between OpenEuler embedded and Zephyr. Number two, embedded virtualization mode. This mode can be viewed as an enhancement of AMP mode. With the help of embedded hypervisor like KVM, Archon, or Zen, strong quality and dynamic resource management can be implemented. Number three, libOS model. As we know, Zephyr can run about POSIX native OS, so it can runs about OpenEuler Linux, provides some kind of lightweight user space multi-thread environment. And other scenarios where Linux is too big. For example, firmware of smart peripherals, BIOS in Zephyr, BIOS in server or PC. Here is the current organization of SIG-Zephyr. I am the maintainer, also the representative of OpenEuler Linux. Hongbo Wang from Intel Shanghai is Intel Zephyr R&D team in China. Guo Liangli, he contribute a lot of Chinese tutorials and docs about Zephyr. Rin Gaomeng, Zephyr ambassador, expertise in Bluetooth field from Xiaomi. Tai Xu, expertise in IoT connection from Amazon China. So SIG-Zephyr makes a roadmap of this year. There are three phases. Phase one is almost done. My talk today, in fact, is part of phase two. Phase three is also on the right way, but it will be a little challenge to implement the virtualization mode of OpenEuler embedded plus Zephyr, considering limited resources. So here, through ZDS, SIG-Zephyr calls for more volunteers to join. Okay, the final part, also the technology part of my talk today. How do we implement OOS mixed criticality deployment of OpenEuler plus Zephyr? First, I want to make some introduction of the background. Taking a motion control system as an example. It was my research field 10 years ago, and it can be found in robots, CNC machines. A typical complete motion control system consists of 3 layers. The top layer, smart control. The top layer, smart control, responsible for work like HMI, plane navigation. The middle layer, behavior control, responsible for work like track trace, collision detect, status monitor. The bottom layer, responsible for the work like motor servo control, sensors, actuators. Different layers has different requirements on flexibility, feature richness, and real time. 10 years ago, to implement such a motion control system, we need a PCB level system, one application processor running Linux for smart control, one microcontroller running RTOS for behavior layer, one or several DSPs or microcontrollers running RTOS or even bare metal for real-time control. Each part has its own memory, I/O, and communications. And each part is connected with onboard bus like I2C, SPI, UART. But the problems of PCB level systems are hardware complexity, several chips and the corresponding memory, power, and clock, low communication efficiency, limited channels and limited rate, low software flexibility because software are located in different RAM chip or flash chip, difficult to develop and maintain because different runtime and different OS are involved. They have different flows. Thanks to Moore's law, the ability, density, and integration of hardware become better and better. Now, the previous PCB level system can be implemented in one system of chip, such as Xilinx UltraScale, where you can find application processor, real-time processor, hardware accelerator, and FPGA integrated together. But the fast evolution of hardware also brings challenges for software. How does software fully utilize hardware resources? Further, how does software define hardware? From the example of motion control system, I want to start the discussion of mixed criticality system, which in my viewpoint is a future trend of embedded system. There are two paths to show this trend. Path 1, from distributed to centralized. Motion control system is one example, also can be extended to smart vehicle, where MCS is very hot here, and it can be proved by the fact that the distributed ECU architecture is evolving to centralized domain controller or zone controller. In industrial IoT, the story of virtual PLC or cloud PLC, where the traditional distributed PLC controllers are deployed in edge, even in cloud, is another good example. Path 2, the evolution of single-node device. With the support of hardware, more features are added, connections, OTAs, especially AI, while the quality assurance of original features like real-time reliability should be kept. For example, the robot arm equipped with a camera become an AI smart robot arm. More and more sensors, camera, laser, sound that are added into drone. So let's go a little further for the mixed criticality system. The criticality here mainly refers to safety, for example, the ASIL ABCD levels in automotive, but it also can be extended to other index like real-time security, power. From the viewpoint of OpenEuler embedded, to implement a MCS, there are three phases. Do the mixed OS deployment first, then implement resource currently, and finally achieve better resource utilization by scheduling. In fact, our approach is a mixed approach of academic concern and industrial concern. In academia, more focus is on the mixed criticality scheduling of shared resources, which comes from real-time scheduling. But let's focus on currently. In industry, more focus on time and space correlating to guarantee the criticality like real-time, safety, reliability. So resources are statically allocated and quarantined. Then you have to face the problem, low resource utilization. In our view, the architecture of mixed criticality system is at the top. The application consists of multiple domains. Each domain runs its own best fit OS or runtime. For example, Linux for management, Windows or Android for UI, RTOS for real-time safety, bare metal for algorithm. At the bottom, the whole system literally runs on multi-core SoC, homogeneous or heterogeneous. And in the middle, the mixed deployment framework is used to deploy the domains and connect domains. The embedded flexible foundation can be based on virtualization, PEE, or other mechanisms. It's used to implement strong quarantine of domains and scheduling of domains. OpenEuler embedded starts its exploration on mixed criticality system from phase 1, the multi-OS mixed criticality deployment. Here, criticality refers to real-time level. In multi-OS mixed criticality deployment, there are three challenges to be handled. Number one, multiple OS integration. We want to simplify the integration of multiple OS, and we using system TTS. TTS means device tree to describe resource allocations of different OS or runtime and their relations. Then using integrated build system to build multiple OS in a unified way and generate the integrated image. For this part, we will do our work based on Yocto system. Number two, the efficient cross OS or cross-domain communications. Because the whole system consists of different domains working together, so the cross-OS or cross-domain communication is critical and is the backbone. So we want to use a IO-based, lock-free, shared memory-based mechanism as the foundation. Then the front end of application is abstract and hardware independent. The back end is flexible, can be software only based or software hardware co-design based. And we will do this work based on openAMP. Number three, service-oriented deployment. On the basis of efficient cross-OS communication, we want to implement service-oriented deployment, where different OS provides its best fit services. For example, Linux provides system management, general network, general file system. RTOS like Zephyr provides real-time control, real-time network, and real-time compute. In our approach, Linux is centric, defines standard interface of management, communicate, debug, and lifecycle, etc. Okay, let's see what we did in the just release of OpenEuler embedded. In the latest release, we implement the basic ability of multi-OS mixed criticality deployment with OpenEuler embedded and Zephyr. Our work is based on openAMP, one core for Zephyr as client, other calls for OpenEuler embedded as host, and we use QMU platform, which is ARM Cortex-A15-7, as a platform of proof concept. And recently, we are working on the support of Raspberry Pi 4B module. Our work consists of 3 parts. In OpenEuler embedded, we did the integration of openAMP and leaf metal in Yocto. Static resource allocation, such as memory for Zephyr, shared memory for communication, interprocessor interrupt, and peripherals. We implement a scheme of kernel module and the user space part according to the UIO framework in Linux, and an echo server demo. In Zephyr, working with SIG-Zephyr, we integrate the build of Zephyr in Yocto and do necessary adaptation of openAMP module support, including port QMU ARM64 platform, modifications of GICv3 driver, and the software generated interrupt-based interprocessor module and the echo client. And we also do some necessary modifications on QMU to facilitate the debug, such as we add extra peripherals like UART and reserve memory. After O3 released, we are working on the scope of O9. We will continue to improve previous work and implement service-oriented deployment. And we also will do the deployment on hardware boards, which is more practical. Our target is Raspberry Pi 4B first, then go for RISC-V boards. About service-oriented deployment, OpenEuler embedded will provide general file system service, network service, library service, and therefore can easily access the rich features in Linux side, and therefore will provide service like shell service, so Linux can access the Zephyr shell by pseudo TTY device, log service, so Zephyr can output its log to Linux and save other file, real-time control service, so Linux can control the tasks in Zephyr like suspend, resume, change pair, or etc. If everything goes well and we have necessary resources, we will challenge the virtualization model of OpenEuler embedded in Zephyr about the embedded real-time hypervisor like Archon and then or what else. Okay, finally, a summary of my talk today. First, OpenEuler, ubiquitous open OS for the digital infrastructure in China, covering cloud, server, edge, and embedded scenarios. Number 2, OpenEuler embedded, a Linux-centric, comprehensive embedded software platform based on OpenEuler ecosystem. Number 3, SIG-Zephyr, a bridge to connect OpenEuler and Zephyr, devoted to Zephyr localization in China and the innovations of Zephyr plus OpenEuler embedded. Finally, the mixed criticality system, the future trend of embedded system, and also the cooperation point of OpenEuler and Zephyr. So in our approach, there are 3 phases to implement it: deployment, then quarantine, then scheduling. Okay, that's my talk today. Thank you very much for listening. Welcome to OpenEuler. Welcome to OpenEuler embedded, and welcome to the SIG-Zephyr. Thank you.